to specify and implement distributed systems. So let me make a diagram. We need the specification. So I'm going to make a nice diagram because it shows everything very nicely. Okay, so the specification has three parts: interface, properties, and model. Properties, there's two kinds of properties: safety and liveness. The model, there's three. No, actually, no. Let me say first, there's the failure assumptions and the synchrony assumptions. For failure, there is no failure. You see, it gets complicated. There's channel failure. Synchrony, there's asynchronous, synchronous, but the one we really are interested in is partially synchronous. Implementation we saw last week, event-based component model. But we're also going to talk about failure detectors. In the no failures, we have crash stop, which I mentioned already before. We have emission, crash recovery, and Byzantine. In the channels, we have fair loss links, stubborn links, and perfect links. So that, I think, gives you everything. So that's all you have to know. Well, so last week we saw this, but we didn't really start writing code. So we saw the ideas for this, that we have layers. On each node, we have layers with messages going down and messages going up. And in between nodes, we have channels. Messages going down, up. The messages going down are called what? Requests. The messages going up are called indications. Wow, great. Yes, they're called indications. So that's what we saw last time. So we're not going to repeat that. So let me go over that. Now, I want to talk about specifying. So the interface, we talked about that. It's the requests and the indications. Now we're going to talk about safety and liveness. This is important. So probably you know this already, right? Can I skip this, or should I say it? Can I say it again, or do you know it already? You know it already? Formally, you can give me the formal definition of safety? Someone tell it to me? No? Specific prefixes? Executions? So you can actually prove mathematically that any property at all is a conjunction. So an AND is a safety, a pure safety, and a pure liveness. It's a very interesting mathematical property. So any property at all of a system, a safety property means that nothing bad ever happens, and a liveness property means that good things happen. You can always separate it into that. So this is a famous mathematical result by Alpern and Schneider from 1985. So I'm not going to give you the proof, but you can find it on the internet if you want to see how it's done. Okay, it's a little bit mathematical. It uses property of topology. We're looking at sets of executions. So a property is a set of executions actually. So it's a property of this topological space. But I'm not going to say why it's true. We're going to assume it's true. Because I want to build on top of this. Okay, I want now to give a formal definition, very precise. So we're going to look at executions, and we're going to define the prefix. So the prefix of execution is you stop at a certain point. The first K configurations with the events. So let's say you have CK here, so it's here, for example. This is a prefix. Okay, with the events. Okay. That's a prefix. So you basically cut off the tail, or it's the finite beginning. It's the first part of execution. That's simple, huh? And then you can extend a prefix, is you take an execution that starts with this prefix. So you can extend it. Of course, there's different ways to extend it. Huh? So you take the prefix and you can extend it to make an execution. So basically that's the basic concepts we're going to talk about to define safety and liveness. So safety, so I'm going to go from the informal to the formal definition. So a property is safety if you want to violate it. If you want to be not safe, then it actually breaks. The system breaks at some point. There is a bad event, such that every execution and behaving up to the bad event will violate P no matter what it does. So basically, this event here is bad, okay? And anything you do after, it will stay bad. So there's a bad event somewhere, and all executions will violate safety. That means you cannot fix the system. When an execution goes bad, it stays bad. So one way of intuition is you take an egg, okay, raw egg, you drop it on the ground, splash. You cannot fix the egg, okay? It's bad, it's broken. So that's safety. Once you're bad, you're dead. Or it's an accident, you crash and you die. Well, that's it, okay? You can't resuscitate after that, okay? So we can make a formal definition of that. So given an execution, so this is the infinite one, and it's unsafe. So the property is unsafe, it's false, safety is false. Then there exists a prefix such that every extension is unsafe. That means if E is bad, is unsafe, then you can pick some finite prefix which is already bad, in fact. So the badness comes in a finite in the beginning, and no matter what you do, it stays bad. Okay, so that's safety when there exists a prefix such that all extensions will also be bad. So basically you have an accident with the car is broken, that's it. No matter what you do after, if you can fix the car, then it's actually not unsafe. Assuming it's a total loss, perte totale, then it's unsafe. Okay? So here's an example. A message sent is delivered at most once. Okay? So this is a safety property because you can break it. Assume the message is delivered more than once. Okay? Which is making this false, So you take the two deliveries and you take the prefix. You cut off the tail after the second delivery, and any way you can extend it, it will always be at least twice, okay? So the property will stay broken. You see? So a safety property you cannot undeliver. It happens, things that happen are irrevocable, okay? So that's an example of safety. That you can break the system. So, okay, now I define the opposite thing, which is liveness. Okay? Again, we can define it with prefixes. given any execution that is alive. So P of E is true. It's a live execution. For every prefix, there exists an extension that it's live. So this is going in the other direction. It's actually kind of do-over. So let me do my example here. Let's say I have here a prefix. Okay, so this execution E is live. PE is true. Okay. For every prefix, that means I can always make it live. I can make this one live. Oh, no, sorry, I'm wrong. There's always a way to make it live. Okay? That means, for example, I'm driving a car. I'm going to the beach. And here I have reached, I don't know, Bruges or something. Okay? Still not at the beach. There's always at least one way to make it after. Okay, there exists always at least one way to make it work. Maybe I still am stupid after that and I don't, but there is always a way to get there. So intuition, as long as there is life, there is hope. When you get here, you can always still make it work if you do the right thing. But maybe not all the ways, So it's kind of opposite from safety. Safety, once it's broken, it's always broken. You cannot unbreak it. But if it's live, you can always have at least one way to make it work. Okay, so that's liveness. So here's the liveness property. A message sent is delivered at least once. Okay, and if it's more than once, it's fine. That's greater than equal to. So that's easy to show. Take the prefix of it, that this is liveness, we can prove it. Take the prefix of an execution. If there's already delivery in that prefix, then we're fine, because any extension will satisfy it. There can be more deliveries, but that's okay, because it's at least one, so it can be more than one. If the prefix does not contain the delivery, then we just have to find an execution where it does. Okay? So, assuming there will be an execution where it does. So a property is liveness if we can always find an execution which has delivery. Okay? So maybe there's failures and retries and everything, but if the algorithm satisfies liveness, even if there's failures possible, whatever, there will always be an execution with the delivery. Okay? So it's property of an algorithm with sets of executions of an algorithm. So if the algorithm is well defined, then you can always find an execution which has the delivery. So the liveness property holds. Okay? So that's safety and liveness. Here's a picture. So I like pictures, so I made a visual way of looking at this. So this is, for me, I like it, it's my intuition, but your mileage may vary. So safety, you can depict it here. So here I have an execution. Okay. If this one is unsafe, then there exists a prefix such that all extensions are unsafe. Okay. Unsafe execution, there exists a prefix where the system is broken. So once it's broken, and so all executions will be unsafe. Okay. And liveness is kind of the opposite thing. So here I have a live execution, and the live execution means that if any prefix I take, for all prefixes, I can always find at least one that will make it true. There's always hope, but there's always a way to make it true. See, so they're kind of dual. They're actually dual in a very precise way. So that's, some people like this diagram, some people don't. So if you like it, you can use it. And you can have a lot of intuition. Safety can only be satisfied in infinite time. So as long as the algorithm is running, it can always break. Yeah? You're never really safe until everything's done, which is only after infinite time. Right? So if I'm running around with an egg in my hand, As long as I'm running, I can always drop the egg. So I'm never safe until it's done, okay? And when I do violate it, it's finite. So when I drop the egg, okay? So never, at most, cannot, partial correctness, those are all safety words, okay? So that's kind of intuition. So liveness is dual. Liveness, you can satisfy it in finite time, when the good thing actually happens. And the only way to violate it is at the end. So if I'm driving to the beach, the only way to be really sure I never get there is at the very end, and I didn't get there. But when I do get there, it's in finite time, okay? So eventually, must, at least, termination is a liveness property, yeah? Those are all liveness words, okay? So we're going to use safety and liveness a lot in the course, and whenever I define an algorithm with the properties, I will ask you, is safety or liveness? So you have to get a good intuition of that. Huh? So here's a question for you. I have defined safety as a property on executions. On execution. So an execution is this sequence of infinite number of configurations. Huh? But why not do simpler? Why not define safety to be a predicate that is true in every configuration? Why not define safety as a property of configurations? Huh? I mean, a configuration is a smaller thing, it's a finite thing, whereas this execution is this big, infinite thing. So why not? Why am I defining safety as a property on executions and not on configurations? This is kind of specification engineering, huh? I don't want you to accept what I say. You can always disagree with me, and we will figure out, maybe you're right, okay? So why don't I? So what do you think? Why don't I just define safety for configurations? Yeah?
In the course calculability, we showed that some problems could not be considered safe because we could not find a right solution.
So you're saying if you do it on configurations, then
you cannot do everything you want.
Then some things you cannot do some things.
Yes.
Mm-hmm. Right? Yes? That's actually a good intuition. So some things that are unsafe, you cannot express them in configurations. So for example, if I have delivery of messages, so the message is delivered at most once. Well, if it's delivered here and here, then if I do in configurations, I won't see that, okay? Because I don't see the message arriving in the inbus. It's maybe already disappeared. So if I look at just the configurations, maybe I don't know. So the answer is because it's very weak. It's not good enough to define it in terms of configurations. Some things I cannot do, okay? So so in fact that's the reason. You can invent lots of properties that you could not define if you do it like this, okay? But execution, it lets you see the whole thing. So you can actually look at the connections between the configurations. So that's why. In fact, this is not such an obvious question, because if you look at books from the 1990s, remember I told you in the 1990s, distributed algorithms was still a very messy science, okay, in those days. And I would have been unhappy to teach it in those days. Some people, some books written by smart people, they did define it like that. So, and eventually people realized, no, it's not good enough, okay? Okay, so that's one thing. Here's another question. So, is every property really either safety or liveness? For example, what about this one? Every message should be delivered exactly once, one time. Is that safety or liveness? What's going on here? Now I'm being a little tricky, yeah? I want to see if you're thinking. So what about this property? Is it safety or liveness? Yeah?
Let's say safety, because liveness would be at least one time.
Liveness would be at least one time?
It's both.
It's both.
It's both?
Because if we are 0, then it is liveness, and if we already have 1, it's safety.
So if it's delivered twice, then it's too much, right?
Yeah. So
Okay.
if we are 0, then we must find a way to have 1, and if we have 1, we must find a way to not have 1 more.
Okay, but a property cannot be both safety and liveness. I mean, you cannot going to the beach and find not having an accident. It's not the same thing. So this is actually, it's neither, okay? If you look at the formal definition. So what's going on here? I actually told you already, yeah? This property is actually neither safety nor liveness. So what is it?
It's a combination of one safety property and one
Yes.
liveness property.
Exactly. It's actually a conjunction.
Conjunction.
Remember, I told you every property can be written as a safety and a liveness. So this one is actually like that. It's at least one and at most one. Okay. Okay. So that's this thing. So which I said, I just asked you the question to see whether you're paying attention. Okay. So this one you can actually define it as a conjunction of both. So this is always true. Okay, so that's the properties. Let me now talk about failures. Failures is really nice because failures is what makes algorithms complicated. Okay. Okay. So when we define our algorithm, it's not enough to do safety and liveness. Okay. We also have to define what is this thing it's running on. What is the network it's running on? The network might have failures. The network might be asynchronous, synchronous. So we have to say, what are the possible failures, for example? We also have to say, what are the possible timing, synchrony? Okay? So the same algorithm, it might not work for synchronous, or it might not work if there's too many failures. Okay? So we have to specify on what system it's running on. Okay? So I'm going to talk about failures now. So failures, there's many kinds of ways of doing failures. Failures, it's a huge number of possible failures. So I'm going to talk about node and channel failures. So the nodes are connected by channels. The channel is the network connection. The node are the computing nodes. Okay, so we're going to talk mostly about these. We're going to talk only about these four. There are other kinds, and because these are important ones, crash stop, emission, crash recovery, and Byzantine. So those are important ones, but there are other ones too. Okay, so a node can fail in one of these different ways. If it does not fail, it's called correct. So nodes that don't fail are called correct, so that's the terminology. So the simplest one, which I mentioned already, is called crash stop. So the node basically just stops, so it doesn't execute anymore. No more state transitions. It stops sending messages and it stops receiving messages. Okay? So the default failure mode, the one we will use most often, is this one. So the nodes do not recover here. They do not recover. That means once a node fails like this, it's dead, okay? And it will never come back. But now let me ask you a question now to make you think a little bit. Now let's take a look at this machine here. And it's running. And the battery is empty. It does a crash stop. And then I charge the battery and I start it up again. So how does that? Is that a kind of recovery? And so it's like a node comes back. So how does that fit into this idea that nodes stop forever? In fact, in the algorithms, we usually will say when a node crashes, it always crashes forever. So if we say that, what happens when we reboot the machine? Yeah? It's a new node, exactly. So the basic assumption is that when you reboot a machine, it will be a new node. Okay? Not the same node as before. Because if it's a new node, and it will actually behave, I mean, there might be some state in that node that is similar to the state of some crashed node, but it's starting afresh. It's doing its execution fresh with messages and so on that it's receiving and sending. So that by default, when a system reboots, a node crashes, it's gone forever, and a node will, if it's rebooting in the real world, we'll consider it to be a new node. Okay? That is the simplest assumption. It's not always true, and it's not always true, and in fact, we'll talk about one case where it's not true, is called crash recovery. But in most cases, like in this machine here, it will be that assumption. Okay? So that nodes, because otherwise the failure mode is more complicated. We have to figure out what is the relationship between the crash node and the reboot. What is being transferred? What's going on? It's more complicated, in fact. But sometimes we need it. So in the case of distributed databases, where we have stable storage, we will use a case where it does recover. Okay? And then we have another thing called crash recovery. But by default, we will assume it's crashed, it's dead forever. Okay? And then there's another kind of failure, omission. This is like temporary glitch. Okay? The node forgets to send a message. Well, it puts an element in the outpuff, which is supposed to be sent, but somehow the outpuff, the element disappears. Somehow, cosmic ray or... But the node is still running, eh? It's just a sent message disappears. Or a received message disappears. So the in-buff maybe goes to empty, or the out-buff goes to empty. Okay? So that's called send omission or receive omission. So basically, the node forgets to send or receive messages, but otherwise it's running fine. Okay? So that's a kind of node failure. Sometimes that can happen. It could happen because of a local, an error, a buffer overflow or something. I mean, it's something that you can see happening sometimes in real systems. Okay? So that's an omission failure. And now I talk about a more complicated one. So this is it's like a crash stop, but now the node can recover. Okay? And that's a little bit more complicated. So the node, it crashes, so it stops taking steps. The state machine does not take any steps, it does not receive and send any messages, they're ignored. And at some point it starts again. It starts receiving and sending messages again and doing state transitions. Okay? And there is a special recovery event. So it knows when it recovers. It knows I'm in a recovery state. So when the node recovers, it starts in some special recovery state. So it knows it's recovering. Okay? It also has a stable storage. That means part of the state disappears when it crashes, but part of the state does not disappear. Okay? So the part that does not disappear is called stable storage. So this is actually modeling a node in a database. Okay? The stable storage is the disk. Okay, and the database, the node of course knows when it's restarting. Okay, and the RAM memory of course disappears when it crashes, but the disk is staying. So why are we inventing this weird mode? Because it's exactly how the node of a distributed database behaves. Okay, like this. Okay? So the permanent device, the disk, will survive and will exist when it recovers. So for example, the node could could save the state to the stable storage. Maybe it crashes and recovers, and then it knows that stable storage. Nothing is lost on the stable storage. Okay? So that's crash recovery. So it's like a formal definition of how a node in a database would work. But it's a little bit subtle, okay? So, because recovery, what if the node recovers and then it crashes again? Ooh, it gets complicated. And what if it recovers, it crashes, and then it recovers the second time? So recovery is kind of a complicated thing. What if I have a database with a node, every 10 seconds it crashes and reboots? That's still kind of bad, huh? I mean, it's like it's coming back, but then it crashes again, and then it comes back, and then it crashes again. So actually, failure is more complicated in crash recovery, yeah? So we say that the node is faulty, so something is wrong. Either it crashes and never recovers, or it crashes and recovers infinitely often. So it's always crashing and recovering. Something you have to worry about when you define this, huh? What happens if every 10 seconds it crashes again and then recovers, and again, and it never stops? So this is kind of being unstable. Huh? It's called an unstable node. Okay? So this is not desirable, yeah?
If there is no question of timing and time lapse, is that a problem that...
That's a good question. So how do we know? Because we're not actually waiting an infinite time here, huh? That is, if you write an algorithm, and the algorithm is based on crash recovery, that means while the algorithm is executing, at some point it should not crash anymore. It can only crash and recover a finite number of times. And so from the point of view of an algorithm that's running on top of this, at some point the node will not crash anymore. Okay? Of course, we cannot wait an infinite time, huh? But from the algorithm's point of view, it has to be that the crash recovery stops eventually. Okay? It has to crash and recover and then stop a finite number of times so that eventually it doesn't crash anymore. Okay? A correct node will eventually do no more crashes. So you can see that crash recovery is a lot more complicated thing than crash stop. Huh? So we're not going to use, this is only used for the implementing distributed databases when the stable storage is really important. Now this faultiness, it can actually happen in real life. Huh? A computer sitting in a data center, for example, and it's very hot. Okay, data centers are usually very hot because in fact Google doesn't care if the computers are crashing because they're all fault tolerant. So it's hot, and what if the computer crashes, or the disk has a problem, or whatever, and it reboots, and it runs for a while, and it crashes again. As long as it only happens once or twice, fine. But if it's happening repetitively, then the node is unstable, and then Google will replace that computer. Huh? Then it's not good. It's a faulty node. Huh? It might be, even things like SSDs have that problem. Huh? You might think SSDs are internal, the solid state disk. They're not. Eventually, you can only actually erase information a finite number of times. So it's very often after some years, especially for old ones, that your system will repeatedly crash. Okay? So this unstable actually happens in real systems. Huh? So the difference between faulty and correct is that that you can still run your algorithms. That's the point. Huh? You can actually still assume that eventually it's not going to crash anymore. Okay? So you can see here that this is a more subtle concept than regular crash stop. Huh? Okay? But it's important because when we build a distributed database, we have to worry about stable storage. Because in a database, you do a transaction. And a transaction is atomic, all or nothing. And it has to be all or nothing always, even if there's a crash at any time. And the transaction is running, and it's a complicated computation, and it crashes. Okay, so part of the transaction is stored in the disk, part is still in the RAM, it reboots. How does it actually work? Okay, it has to be perfect. That means it has to be all or nothing, despite this kind of thing. Huh? So there's actually a trick for transaction. Huh? So while the transaction is running, you actually keep the old state on the disk, and you store the new state. You're building the new state as the computation goes on the disk. And on the disk, there's a single bit, which is either 0 or 1. And the bit either points to the old state or to the new state. And when the system crashes and reboots, you read the value of that bit, and it tells you whether to keep the old state or to use the new state. Okay? So that's how it's implemented. And it works with this kind of model. Okay? So it's actually quite complex. I'm telling you, it seems simple the way I say it, but actually making it really work is not so simple. Okay? So crash recovery is the most complicated one. And we're not going to use so many algorithms. We maybe have 1 or 2 algorithms that are going to use this model. But if you are working with databases later on, you will see that a lot. Huh? Okay? And the final one is the worst one of all, Byzantine. So I mentioned it already. Right? The node may do arbitrary behavior. And in fact, it's really, really bad because several of these bad nodes, they might collude, which means they actually work together as a team to break the rest of the system. They can be arbitrarily bad, okay? So this has become more important nowadays because of cryptocurrency, okay? So 20 years ago, this was more academic play thing. But nowadays, there's lots of money hanging on this algorithms, okay? So the crypto blockchain algorithm, of course, is a Byzantine algorithm. It's a Byzantine consensus algorithm, and it can do transactions. Huh? So maybe this year I will, in the second half of the course, say something about that, because this is now becoming very important. Huh? But otherwise, we're not going to see so many Byzantine in this course. Huh? I mean, you would need a whole course just for that. Huh? Okay. So there's actually a hierarchy. These 4 different ones, they're actually, each one is a special case of the next one. Okay? So for example, crash stop is a special case of emission. So emission, if after a certain event you omit all sends and receives, then it's exactly like a crash stop. Huh? So a crash stop is a special case of emission. Emission is a generalization of crash stop. Okay? Also, we can compare crash recovery and emission. This is more subtle, okay? So we can actually make a version of crash recovery that is exactly the same as emission. So assume a special case of crash recovery where I'm only using the stable storage, so no RAM, just the disk. And in that case, crash recovery is identical to emission, because when it crashes, it's omitting the send and receive, and when it recovers, it starts using again the send and receives, but the state is still there. So it's exactly the same as if it was just forgetting the sends and receives. Okay? It's the same as emitting, send, and receive while being crashed. So crash recovery with only stable storage is actually identical to emission. Huh? Okay? Now, if you have a more general crash recovery, where you have not only stable, but you also use volatile memory, so the memory that goes away on the crash, the RAM, then the recovered nodes, of course, will forget something. So we can see that crash recovery is actually the same as emission plus something you could call amnesia. Part of the state is forgotten. So it's like emission, but you also forget part of the state. Okay, so that's, you can consider crash recovery to be like that. Okay, so emission is actually a special case of crash recovery, huh? Where you only have stable storage. You see that? How that works? We're actually trying to understand better the connection between the different failure modes. Huh? So emission does not have amnesia. You don't forget any state in emission. Huh? You're just forgetting sends and receives. Whereas crash recovery can also forget part of the state. Okay, that's the thing. That's the new thing with crash recovery. And of course, Byzantine, everything is a special case of Byzantine. Huh? So in fact, we have this diagram. Huh? All crashes are a subset of emissions, subset of crash recovery, subset of Byzantine. Okay? So if I have an algorithm that works for crash recovery, it will also work for emission. And it will also work for crash. Okay? If I have an algorithm that's designed to work on emission, it will also work for crash. And a Byzantine algorithm will work for any kind of system. Okay? So why don't we do always Byzantine algorithms then? Because they're very slow. Okay? Extremely slow. So in many cases we don't do this. We try to avoid them for that. Huh? Okay, so that's the fault tolerance. So in this course, most of the time we're going to be here. Okay? And we'll talk a little bit about this one. And maybe, if you're very nice, we'll talk about this one in the second half. If you want me to, I will prepare some lecture on blockchain. Maybe you like that. I don't really get why people consider there to be value in that. I don't recommend you buy bitcoins, but I can explain how it works. Okay? Okay, so now we have only part of the failures. Huh? We have these failures. We also have channel failures. But channel failures are easier, actually. Luckily. Okay? So basically, channel failures. So the basic channel that we're going to talk about in this course is called a fair loss link. The channel delivers any message with non-zero probability. Okay? So we're assuming non-network partitions here. That's another thing which maybe we'll talk about. We just have channels that can sometimes drop messages. So in fact, the whole course is built on top of that. So remember in a previous lecture, I said, look, there's a magic rule that lets you make a message go from out buff on one node to in buff on another node. So we're assuming that as a fundamental thing, and we're building on top of it. Well, in fact, we're assuming a little bit more than that. We're assuming that the message could also disappear with some probability. Okay? That when the message goes from out buff to in buff, there is some probability, some number between 0 and 1, that the message poof disappears. And so that's called a fair loss link. So I'm not going to show you how to implement this. This is Olivier Bonaventure's work. Okay, he has told you that. So for example, IP does this. And the whole course is built on that. So you could see it like this. Fair loss links. That's the basic concept. And the whole course is built on that, okay? We're assuming that exists. All the algorithms we do are going to assume this. And so that is something that's out of scope. So someone else's problem, okay? Someone else has implemented this. But we're going to do lots of stuff on top of that, huh? So I'm going to show you some code. So the message that drops with some probability is not so nice. I actually don't want that. So I'm going to define perfect links. Any message sent will be delivered exactly once. So I will show you the code. So we're going to start writing code in this model for this. And the code will have two layers, and it's an intermediate layer called stubborn link. So the simplest code is actually with two layers. So stubborn and perfect links. Okay? Yeah?
Can you describe the difference between fair loss and stubborn links? I don't see the difference.
Fair loss and?
Stubborn, sorry.
Fair loss, I send a message, it either arrives or it does not arrive. Okay? Stubborn link, I send a message and it arrives infinitely number of times.
Okay.
Okay? It's coming and it never stops. So why am I doing that? Because it seems kind of stupid, but it makes the code very simple. So it's very important in this course to keep the code simple, okay? Once you have simple and correct code, you can always optimize after. You never want to optimize in advance, okay? So stubborn links make the code very simple, and actually they are sort of useful. There are actually uses for them in databases, okay, where you have to send updates. So here's a fair loss link. I'm going to give it a name, FLP2P, fair loss point to point. So this is the send, this is like a record. It's a type with a PJ, so it's going from PI to PJ. There's a message M. And here I have the deliver arriving. So this is a deliver event coming from PI with M. So I send a message, and the message is delivered. Okay? One node I send, on the other node I deliver, and I can do the other direction. Bidirectional. So this thing is assumed. I assume this exists. I'm not going to show you the code for this. Okay? You have many courses showing you code for that, IP, all that. But I will show you the specification of this. Okay? So specifying this. So this is called fair loss point to point. There is one request and one indication. So the request is a send going down on a node, and the indication is the delivery coming up on another node. Okay, and each one has two arguments. So this has the name of the destination node and a message, and here is the name of the source where it's coming from and a message. Okay, so that's the interface, very simple, and it has three properties. So this I'm going to do out through the whole course. I'm going to define the interface and I'm going to give you properties. So these are the three properties. So they're called FL1, FL2, FL3. So FL1, fair loss. So these properties, I'm going to write them in English, but in fact they're formal properties. If M is sent infinitely often by PI to PJ, and neither of them crash, then M is delivered infinitely often by PJ. So that means if you keep sending M on one side, infinite number of times, so forever, it will keep arriving on the other side. But it doesn't say that it arrives the same number of times, here. So there could be lots of losses here, could even be infinite losses. You see that? And even the probability of loss could change over time. It's not like 10% of messages are lost. It could be in the morning there's 99% are lost, and in the evening only 1% are lost. And it would still satisfy this. You see, I'm not actually talking about probabilities here. So this is just a property that if I keep sending, messages will keep arriving. Yeah?
We are here considering only one message.
Yes.
So
The same message.
If you deliver two messages,
We're only talking about one message here. So if I have two messages, then FL1 holds for each one of them.
okay.
If I send M infinite number of many times, then it will arrive an infinite number of times. That's one message. If I have another one, M2, then the same thing will hold for M2. Okay? This holds for all messages. Okay? And then there's another message. So this is not enough, of course, huh? Because if you only have this property, a lot of bad things can happen still. So we have more properties. Huh? So the second one is called finite duplication. If M is sent a finite number of times from PA to PJ, then it is delivered a finite number of times. A message will not be duplicated infinitely many times. So you can't just send a message once and it arrives infinite number of times. No. But you can send it once and maybe it arrives twice. That's okay. That's weird, huh? So if the sending is finite, the delivering is also finite. So why do we define this like that? Well, one reason we define it like that is that if we define it like that, it's actually all the rest is very nice. But that's not enough reason, huh? Because the real world protocols will be like this. If I send a packet on IP, it might arrive twice. It might. It might actually go into one router, and then the router sends it to another router, but then the router thinks that the other one has crashed, but it has not crashed. So it sends it, it routes it, so it might go on two paths, and it might actually be delivered twice. Or any number of times with a low probability. Huh? So this is actually a real property of a real system. Okay? Finite duplication. And then we need one more property, no creation. No message is delivered unless it was sent. Which means the network is not allowed to invent messages. Okay? So if we have these three together, this is a very close specification of how real-world networks behave. Okay? This is fair loss links. These three properties. And each one of them is intuitive. Why do you have all these three like this? There are other ways to define this. Huh? It's not the only way. But this is a nice way because it actually separates out things. So the network cannot create. That's reasonable, huh? The network will not infinitely duplicate. So these two properties mean that the network is not doing weird things, okay, in a sense, huh? It's not creating random weird messages. That's FL3. And it's not going to be infinitely duplicating a message. It might finitely duplicate, but that's okay. We could say if it's sent once, it's delivered once. But that's not good enough because real IP is not like that. Huh? Real IP could deliver twice. Huh? If you have read carefully the course of Olivier, you know that that's true. Huh? So this is actually more reasonable. The network will not infinitely duplicate. So these two are saying that the network is actually nice. That's what these two are saying. Huh? And the first one is saying is that actually the messages will arrive, okay? You don't know when, really, but they will arrive, okay? And then maybe one question now before we do a small break. So these are three properties. So which ones of these are safety and which are liveness? That's a question for you. Huh? FL1, safety or liveness? What do you think? Liveness. Why liveness?
Because it will arrive eventually.
So F1, you can only satisfy it after infinite time. Is that right? Or what? Can you break this? Can you break the system with F1? Can I have one event that breaks? No, what? is delivered infinitely often. And you can always, so if I go up to a certain point, the idea is I can always find an execution where it's delivered again. Huh? So the point is, in terms of prefixes, I'm assuming a prefix and it's delivered here a couple of times maybe. And then to make it be infinite, it would have to be more times. But I'm assuming it's sent infinitely often and it has to be delivered infinitely often. Okay? So this is a Liveness property, yeah? What about FL2? Liveness or safety? This is more subtle, huh? Can you break the system in finite time? That's a question with this one. Can FL2 be broken in a finite time? No, huh? So for it to be safety, you have to be able to break it, huh? So this is not a safety property, huh? So you cannot duplicate a message infinite number of times, huh? So what about the third one? Safety or liveness? Safety, why? Yeah?
Because when a message arrives, the system is broken.
Exactly. If some random message that was never sent arrives, the system is broken, huh? You can break it here, huh? And actually, you know, if these two are liveness, it has to be safety, huh? You can't have only safety or liveness. You need both, huh? So that it's clear there has to be at least one of these has to be safety and at least one has to be liveness. Otherwise, my specification is not good. Huh? It's incomplete. Huh? I need both. Okay, so the third one is safety. Huh? Okay, so everything is built on this. So we assume this. Okay, this is the bedrock. This is the foundation of the whole course. Is this, in fact? All the algorithms we define in the course are going to be built on top of fair loss links. It's amazing, huh? How much you can build on top of a simple thing, huh? But this is actually not so simple, huh? Proof, ask Olivier, huh? He will tell you it's not so simple, huh? Okay, so we make a small break, and then I'll start writing some code. So we're going to build on top of fair loss. So I'm going to show you some code now. So we're going to build, I want to build perfect links. So this is the one we're going to use for many algorithms. Huh? But the one that we get from the network people is this one. So we need to build this one. So I'm going to write some code now. So the best way, the simplest way to write this code is to make an intermediate layer between fair loss and perfect. So fair loss can lose messages. So the stubborn links kind of overcomes that by making sure the messages arrive. A single message arrives infinite number of times. So that will overcome the loss. But then it can arrive more than once. So that then there's another layer to make sure that you only accept one of those infinite ones. So the simplest code is 2 layers. Okay? So in the stubborn links, the interface is the same as before. Stubborn point-to-point send and deliver. And this time there's 2 properties. Okay? Stubborn delivery and no creation. So here we have clearly an infinite delivery. If PI sends a message M to a correct node PJ and PI does not crash, then PJ delivers M an infinite number of times. So that basically you send and the message is arriving forever infinite number of times, and there's no creation. So it's a little bit simpler than fair loss because there's no finite duplication property here. Here all the messages arrive infinite number of times. Okay? So again, there's safety and liveness in there. So we're going to implement it. So I'll explain and then I'll show you the code, and that'll be kind of the first code we see. So I'm going to use fair loss links. The sender will have a local set of messages called sent. It will store a message as sent and will periodically resend the messages in sent. Okay? And with this code, we can actually prove that the two properties hold. Messages will be delivered infinitely many times. The lossy link can drop messages, but not an infinite number. Okay, it can drop a large fraction of them. But if there is an infinite number being delivered, there will be an infinite number arriving at the other side because of the lossy fair loss property. Okay? So you could define stubborn links in the formal model too. Just show you how you could do that. So here's an execution. CO, C1, C2 with events. So if the message appears in the outbuff of P for some link, okay, the idea is that del ijm will happen infinitely often without removing m from the outbuff. So the message will always stick in the outbuff. Even if you transfer it to the inbuff, it will still be in the outbuff. So basically it will be sent infinite number of times. Okay? So that's one way you could model it. So here's the code. So the code is basically 2 pages. So this is code. This is the first code. So this is stubborn links. It uses fair loss links. So this is the code. So it's a 2-layer system. Okay, I have fair loss link here. I have stubborn link here. I have the request indications are like this. This is on one node. I have another node here. Okay, so it's like this. This is a channel. There's a channel underneath here connecting these. So this is already a system with 2 layers. So the stubborn link is built on top of fair loss links. It has a local variable. So the way it works is that there's always an init event on startup. The sent is a set. So I'm going to assume all the data types I need. Pseudocode. So sent is a set that starts being empty set. I will also assume there's a timer, start timer. And then after some time, there's a timeout event. And then for all destinations and messages, element of set, do, trigger, fair loss point-to-point send. So I'm going to send all the messages in the send set, and then I start the timer again. So every timeout I will do again. So this will go forever. Okay? So that's the first part. And the second part is this. What does the stubborn point-to-point send do? It just adds the message into the send set. That's all it does, one line of code. And what does fair loss point-to-point deliver do? It just does stubborn deliver. So basically, the fair loss point-to-point deliver is this, and the stubborn deliver is this. That means when I receive this message, I will send this one. Okay? And that's it. That's the whole code, Simple code, right? That's all my code. This plus this. A few lines of code. You see how it works? My 2-layer system? No problem? Okay, great. Great, because later on it gets a little bit more complicated, but not that much more. So here's perfect links. So this is the final one. This is going to be another layer on top here. Basically, my system will have 3 blocks. So the real system will be like this, So the perfect links are built on top of stubborn links. Here I have perfect point-to-point. So this one will actually deliver the messages exactly once. So there's 3 properties. Reliable delivery, no duplication, and no creation. So these properties are very nice, okay? They're the ones you really want in an application. So reliable delivery. If PI and PJ are both correct, then every message sent by PI to PJ is eventually delivered. Perfect. No loss. No duplication. Every message is delivered at most once. Okay. That's great. Not more. And no creation. The network is not going to create messages. That's all I need. So I send a message, it arrives exactly once. Okay? Okay, again we can play the safety liveness game, So, very quickly now, you know, every message sent by PI to PJ is eventually delivered by PJ. What is that?
Liveness.
Liveness, huh? Of course it can be delivered twice, we don't care. Huh? Every is delivered at most once. What's this? We've seen it already, huh? At most once. Come on, you guys. What is it? I'm not hearing very clearly here. Safety? Really? Yeah, maybe. It's on the slide, it must be right. And the final one? Unless it was sent. That's, you can break it easily. So that's safety. So that's it, huh? So then I'll show you the code now for this. So the implementation, you can actually prove. Here, the implementation is the receiver is doing the work. Remember, in the stubborn links, it's the sender that had this extra set. Here, it's this receiver will keep a log of all received messages. And it will only deliver a message up if it's not in the log. Okay? And you can actually prove the three properties by reasoning on the code and on the stubborn link properties. Okay? So reliable delivery, you know it's going to be delivered at least once because the stubborn link will deliver at least once. Okay? In fact, stubborn link will deliver infinite number of times, so there's no problem. No duplication is because of the log, and no creation is also a stubborn link property. Okay? Well, let me go here and show you code. I think that's it, It's only one page, this one. So here, implement perfect link, use stubborn link. There's a delivered set. Okay? It's used for the sender. So I do a perfect point-to-point send, and I do a stubborn. So when I get this request, I send downwards. And if I get a stubborn point-to-point deliver going up, if M is not in the delivered set, then I do a trigger. So I make the message go up, and I add M. So this will guarantee that M will only be delivered once. It's very simple, huh? So basically, when the message comes up, it will do a check here, whether it's in the delivered set, and if it's not, it will do this, otherwise it will not do that. Okay? So that's very simple, huh? So now we have this three-layer system building on top of fair loss, doing perfect point-to-point. Okay? Okay. So compared to the course, so in the rest of the course, we're going to assume perfect links. Okay? So I did this because real-world networks are usually more doing like this. Whereas for the algorithms we want, we kind of like this one, perfect links. Okay? Messages exchanged between correct nodes are delivered exactly once. Okay? We will also assume that messages are unique for the rest of the course. So the message identifier includes the sender's identifier. Also, if the same message is sent twice, the same content, we're going to assume it's two different messages. So each message is unique. That's what we're going to assume for the rest of the course. Okay? So stubborn links are not that much used in practice, really, but they are used in crash recovery, actually. Because for databases, it can be useful to try more than once. Okay? Okay. So this is, of course, not the most efficient implementation, but it's correct. And it's actually easy to prove that it's correct. Prove it, huh? If you look at TCP, so you all know TCP, right? You do know TCP, yeah? So TCP doesn't work like this, really. It's more complicated. So how does TCP keep track of the messages, or let's say the packets that it receives? How does
three-way
it do that?
handshake.
Sorry?
The three-way handshake.
Handshake, but how does it know that it received certain packets and did not receive others?
With the acknowledgement.
It has an acknowledgement. It has sequence numbers, huh? it numbers the packets, huh? So everything is numbered, and it has this sliding window thing. So it can have more than one packet in flight at the same time, and they can arrive out of order. Doesn't matter, because they're numbered, the packets. So that's a performance optimization, huh? So we don't implement that here, huh? Okay? And the sequence numbers avoid the need to keep all the messages. A sequence number, I can actually have a number that says I have received all previous packets up to 950 or something. Huh? So this one number replaces a whole set. So you see, TCP is doing lots of optimizations, okay? Whereas in this code, there's no optimizations. Huh? But if you want to prove correctness of the real TCP algorithm, it's not so easy. If you really want to prove it, it's doing lots of optimizations, okay? Whereas the proof of this is trivially easy. Now, in this case, it does not make so much difference yet, but once we start doing fault-tolerant consensus algorithm using partially synchronous systems, the algorithms will be getting more subtle. So that means it's very important not to do these optimizations in the beginning, okay? So we're going to present algorithms in the beginning that are not optimized, huh? But we see they're correct. It's very important to know they're correct. Huh? There's a famous computer scientist, he's not the only one who said this, but he's one guy called Oosterhout. He actually was one of the guys who did this raft algorithm. He did many things. He did Tickle TK. He said the biggest increase in performance is when your system goes from not working to working. It's true, huh? So don't worry about optimization. I know it's very, very hard not to worry about optimization. And I have spent many years optimizing things. So I love optimizing, okay? So I had to unlearn a lot of that when I start building more complicated systems, okay? So that's just an advice. So now let's talk about synchrony. The different models of synchrony. So there's the three models, okay? Synchrony tells us, basically it's talking about speed, message transfer time, computing time, and there's three basic kinds of systems. Each of them has a formal definition: asynchronous, synchronous, and partially synchronous. So the asynchronous is the simplest, which we saw, and the model that I presented is actually doing asynchronous. So there are no timing assumptions on the nodes and the channels. That means processing time can be arbitrary, and transmission time of message also, there's no bound. It can be arbitrary but finite. Huh? So our formal model assumes no time. The only thing it assumes is causal connection. You say that, you remember that. That's the only thing we really, really know. And in asynchronous system, that's the only thing you know, is causality. And you can observe it using Lamport clocks or vector clocks. Okay? The total order of all events in the whole system running on planet Earth, okay? So let's say I have 1,000 nodes talking to each other, and there's events happening on every node, and I want to know the total order of all those events. That is extremely hard. It's not observable. Even if you try to do clock synchronization algorithms, it's incredibly difficult to do that. So basically the total order of all events in your whole system, I'm saying total order in terms of clock time, nanoseconds, this event happens now, 35 nanoseconds, there's another one, etc. This is not observable, okay? If I have a hardware clock, so it is not easy. Hardware clocks are extremely hard to use in algorithms. Synchronizing hardware clocks on different systems is extremely hard. So most algorithms do not assume that for correctness, okay? You can assume something about clock for tweaking the performance, but not for the correctness, okay? So then the big question, of course, is the internet asynchronous? So you already have some idea about that. So you already have, this is not such a simple question. Is the internet asynchronous? So what do you think now, after we've had a few weeks? Is it internet an asynchronous system? What do you think? Is it? Or not? And is it a good thing for the internet to be asynchronous? You tell me. Anyone has an idea now, after several weeks? I mean, I don't want just yes or no answer. Right? This is a big question, and it opens a lot of things. There's a lot of things around that question. First of all, if the answer to this were yes, then many algorithms would be impossible. If this was really yes. But if you look at the internet as it exists, you could assume it's asynchronous, right? In fact, you can assume any distributed system is asynchronous. You just ignore the bounds. But it's clear the internet is not synchronous in the sense of very small, tight bounds, right? So this is not such an easy question, Nobody wants to say something here? What do you think when you say that? No? I mean, so it would be very bad if the internet was a most general form of asynchronous system. But theoretically, it is asynchronous. If you look at something like IP, best effort protocols. But in practice, it's not really, it's actually a very mild kind of asynchronous system, which we'll call partially synchronous. So that's a big question. So it might, this kind of question can appear on the exam. Okay. So the other side is synchronous systems. So the idea is that there's an upper bound, but a known upper bound on the node processing and a known upper bound on the message transmission. So typically these are very small systems, multi-core. The cores, there's a known bound between the connection between cores. Also like clusters with very fast backplanes, known bounds. Local area networks in buildings also usually have known bounds. Okay, so these tend to be small systems. And because they're very close together, it is sometimes possible to synchronize the physical clocks, hardware clocks. But it's not so simple. You have clock drift. So at the level of a computer running at several gigahertz, the clocks will not be easily synchronized. They will drift. So one of them will be a little bit faster or slower. They will vary with temperature. Okay, unless you have atomic clocks in every machine, and you don't have it. So these are quartz clocks, and at the level of a computing system, quartz clocks, they vary a bit. So you have clock skew, which means that even on a single board, a chip, there's one clock, and the clock is connected to different parts. Because the distance is different, there can be they can be not synchronized. So this is called clock skew. So when you build a microprocessor, you have to worry about that. That the lines, the feeding it with the clock are very, so it's very hard to design that. So physical clocks are no miracle solution. So why do we study synchronous systems? This is an easier question than the previous one. Why? Why? Why is that an interesting system? Why is that interesting? There's several reasons. You have to at least tell me one or two. Come on. Yeah?
They are easier to...
They're easier. Yes. See, that's a good reason. They are easier. Algorithms of this kind of system are very easy because of the known bounds. And so in this course, we will very often present you an algorithm on a synchronous system. And then we'll try to make it work on a partially synchronous system. And sometimes that works, sometimes doesn't. But it's good to start there. Another reason is that small systems are synchronous. So these systems do exist, okay? A system that is physically small can be made synchronous. Of course, a large system cannot be made synchronous because of the transmission, the distance, okay? So the internet is clearly not synchronous, but a small system can be made synchronous, okay? So that's another reason, because they really do exist, yeah?
If we can, should we always make a system synchronous? Or is it really a trade-off?
Well, there's a trade-off. It costs engineering effort and money to make systems synchronous. Okay, you have to, the different pieces of the system have to be coordinating with each other. That's easier for a smaller system to do. It's possible, but very hard for larger systems. So these systems can be, the bigger they are, the more expensive they are, the physically bigger they are. Okay, so smaller systems can be made synchronous, and it's not too expensive. And because the algorithms are easy, that's what you do, okay? So it's a trade-off. It depends on the size of the system and the money you want to put in, okay? But asynchronous are the worst, okay? Asynchronous, the theoretically asynchronous ones, are the hardest. And many interesting problems are impossible, like consensus, which you saw in the first lecture. So it turns out that we are lucky. So God has been nice to us, people building the internet. The laws of physics are nice for some reason. I don't know why. It's a big mystery. But the internet is not actually an asynchronous system purely. It's more like this one, partially synchronous. So what does it mean? It's actually kind of subtle. It starts out being asynchronous. So when you start running your algorithm, you have to assume it's synchronous because the bounds are totally unknown. But eventually, there will be bounds. Okay? And so it becomes synchronous. In every execution, some bounds eventually will hold. The point is, you don't know when, and you don't know what the value is. So there's still a lot of unknowns, huh? But because of this, we can actually build real systems. Your algorithm will have a long enough time window where everything behaves nicely. By nicely I mean synchronous, so that it can achieve its goal. Okay? So a partial synchronous system is a system that starts out being asynchronous, and after some unknown time, but finite, it becomes synchronous. So there are bounds, but they're unknown. That seems to be very, very vague, kind of a... There's still lots of unknowns there, huh? But it's enough. That's enough for us to build real things. It's interesting, huh? So we see that in this course. Huh? So are there such systems? You should be able to answer that, huh?
Internet.
Internet, yeah. Internet is a typical example of... It's the main one, huh? And the reason why the internet is like that is because the internet is hierarchical. So when two nodes talk together, they start by using only local routers, and those local routers have bounds. But because of various issues, congestion, errors, failures, whatever, routers that change, it's not guaranteed that it will stay local. It may go to another level in the hierarchy. Yeah? So internet is kind of a hierarchical system. Let me make a picture. So I have two nodes talking together. So usually they will use only local routers, but not always. They might use routers a little bit farther away, or even a little bit farther away than that. Okay? So it's hierarchical. So 99% of the time, the local ones will be fine, and so you will have bounds here. So it's synchronous. But sometimes you will not go here, you have to go out. And so the bounds will increase. So maybe this is 10 millisecond or 1 millisecond. This one is 10 millisecond. This one is 100 millisecond. So maybe 99% of the time the bound is 1 millisecond. But 1% of the time it's 10 millisecond or 100 millisecond. Maybe, and it really happens. Sometimes the messages get rerouted far away or they get stuck. They get stuck in a router. Maybe there's a huge amount of congestion in this router here, so that the message slows down a lot. So that also will slow things down. So what that means is that very often the bounds are known, but not guaranteed. And if they're not known, it goes to the next level. Okay? And if those are not known, it goes to the next level. So that's exactly kind of how a partially synchronous system works. Huh? Eventually there are bounds, but you don't know what they will be. Okay? So the internet is typically a partially synchronous system. So here's one way of seeing it. So my algorithm starts running here. So this is time. And it starts running and its system is asynchronous. So I have no idea what the bounds are. Messages can be long. But at some point, the system starts behaving synchronously. There are bounds from this point on. Okay, there are bounds, even though I don't know them, they exist. So that means messages will have bounded time. So the algorithm will be running in this point, and at some point the algorithm terminates. So the basic idea is that the algorithm has to survive this phase, and during the synchronous phase it can actually make progress. Okay? So this can seem, yes?
Is it possible that from the synchronous side, like for a fail that we saw, it goes back to a synchronous?
No, because then you're just pushing this. So if you're here, okay, and all of a sudden there's a problem, and the bound and it goes way up. It's like this line is now here. Huh? You see? So this line is always at one point. But if you think you're synchronous here, you might not actually be, because maybe here you will break one of these bounds. So what that means is that actually the system is only synchronous from here. Okay? See, that's why there's only one point when it's synchronous. But that point, you don't really know where it is. But there will be a point at which there will be no more exceptions after. You see, there will be some point here or maybe here, and after that, you will stay in the bounds. That's the point. Okay? So we assume that it won't always be exception on exception forever. It will stop being exception. At some point you will go to a level and the whole thing will be running inside that circle. So that's what we assume. And that's what the real system actually does. It will never keep escalating forever. First of all, because there's no forever, and because the chance of it doing so really gets lower, much, 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 much lower, okay? So maybe 99% of the time it runs here, 1% of the time it runs here, 0.001% it runs here. So you see, it really is like this up to a very high probability, okay? And then, once you get up to 99.999 or something, then anything can happen, of course, huh? Lightning can strike, of course, on this machine too. At that point, we're fine. If at that level of reliability, we're fine. So this model is extremely good. It fits to very high probability, the real behavior. Okay? So in some sense, we're lucky that the internet is like that, because the laws of physics are like that. Because things that are close together are talking fast. And also, the internet is a best effort. It's a loosely coupled system. So you can have problems like congestion. And if your internet is under designed, if the system is overloaded, then most of the time this guy will be jumping here. And if it's really, really badly designed, then nothing's going to run anyway, okay? So you need a certain minimum capacity so that things can actually run. Once you have that, then you get to this level, huh? Okay? So that kind of explains how the internet, so that everything in this course is based on that, huh? So, in fact, let me give you one more small thing, and then we'll stop. So we're almost at the end, but let me explain how this connects to failure and to the rest of the course. Okay, so I'm just going to start now a little bit. So the second part of the code is called failure detectors. Okay, temporary. See, synchronous. Okay. Okay, now I just want to give you the intuition for the next step. So this partial synchrony, okay? You don't want in every algorithm that you write to model it again and again and again in the code, okay? So you want to move that out. So all of the complicated stuff of figuring out whether it's synchronous or not, you want to move it out of the algorithm. So the idea is you introduce a concept called a failure detector. Okay, this was a very important invention. So I'll show you on the next slide really what it is. It's a very simple idea, and it was invented around 1990. You can see a lot of stuff happened 1990 to 2000. Huh? It took a while for everyone to use it. It was a major step toward writing the algorithms in a simple way, okay? As opposed to a disorganized bunch of complicated algorithms, which what it was in the 1990s. Okay, so let me just give you one picture here. So this is a failure detector. It's just a box running some code, and it only gives you output. There's messages coming out. That's it. And there's many different ways of doing this, but there's two. The basic one is called P, which means perfect failure detector. It tells me when a node PI has crashed. It's like an oracle. So I'm sitting here and saying, it tells me the node over there has crashed. So it sends me a message. It's telling me when nodes crash. So that is called a perfect failure detector because it's telling me perfect information. Okay? It's called P. But then there's another one called eventually perfect. This symbol here, this diamond symbol, means eventually. So this is simple coming from temporal logic. So you read it as eventually perfect. This is the one that's connected to partially synchronous systems. There's two possible messages here. Suspect PI and restore PI. So it can say, I suspect P1 has crashed. Okay. But then, a little bit later, it can say, no, I was wrong. In fact, P1 is okay, so restore P1. So it can send me two messages. It suspects nodes, or it no longer suspects them. Okay? So as long as the system is asynchronous, this guy can make mistakes. This is the guy I'm using for partially synchronous system. It can make mistakes. It can suspect a node, but in fact it's not crashed. It's just a little bit slow. But after the system becomes synchronous, it no longer makes mistakes. So at some point, this guy stops making mistakes. So this is the building block, okay? So I just want to say now one more thing. So in this course, we're going to write many algorithms that are built on top of P, and many algorithms that are built on top of eventually P. So these ones on the left are the algorithms that run on synchronous systems. This is typically a synchronous thing, where you know when nodes fail, and this is the partially synchronous version. So we're going to try to write algorithms that work for this case. And that's really the real heart of the course, so the interesting thing. It's this one here, okay? And we try to go from here to here. So one approach is to write an algorithm for P, and then try to tweak it so it works also for eventually P. Sometimes that works, sometimes doesn't work. Sometimes you have to be very smart for this one. Sometimes you don't. So that's really kind of summarizing the course, going from P to eventually P. And this is the internet case. So all of the big internet systems, Google, Facebook, whatever, they all are sitting here. They won't really tell you that. Maybe many of the employees, they won't even understand it themselves, but the system builders, they will understand that. So all of the big internet systems are sitting here, okay? So the point is that at the end of this course, you will also be here. That's my goal. Okay, so let me stop there.